Okay, so I'm just going to begin now. I think I have all that I need. Okay, so I believe we ended last lecture talking about rank and a little bit about the connection between ax equals to 0 and ax equals to b, and I think I've done that to death now. And so now we're going to finally put together all of the things that we do know about linear systems, and we're just going to combine all of it and figure out so far what can we say about linear systems, square linear systems, and even at this point, I'm now willing to talk about uh, systems that are not square, systems that have more equations or systems that have more unknowns. Okay, so here's the idea. The idea is as follows. So we talked about the rank, and the rank was, I said, the rank is the number of pivot variables, right? So the number of pivot variables is the rank of that matrix. So when you do Gaussian elimination and you get some pivot variables, then the number of those pivot variables is the rank of that matrix. Okay. And so let's talk about square systems. Let's talk about a square system. And a square system, of course, means there are n equations and there are n unknowns. Okay. So n equations and n unknowns. Now, a square system, of course, gives rise to a matrix. So for example, if I say ax equals to b, then, or ax equals to 0, right? Ax equals to 0. This is a homogeneous system, and this is a non-homogeneous system, right? And so a square system gives rise to a matrix, a coefficient matrix that is itself square, which means this is an n by n matrix, and this is also an n by n matrix. Okay. So what can we say about this n by n matrix? So let me just draw a schematic of an n by n matrix. It's a square matrix. It has n rows and n columns, right? So this is A11, A12, and A1n. That's the first row. The second row is A21, A22, up until A2n. And then we end at the last row, which is n rows an1, an2, and an. And these are the n square entries of this matrix, right? So this is n row n. And as an example, we can consider, of course, the 3 by 3 matrix, right? Think about a 3 by 3 matrix, because that's something that we've dealt with. I'm not going to put entries here. I'm just going to put a star here because these stars are going to change, and we know what we're talking about, right? Okay, so now let's think about the possible rank of this matrix. What's the possible rank of this matrix? Now, when you do Gaussian elimination, the first thing that you try to do is get rid of these two entries, right? You try to make this into a 0 entry, and so you try to get rid of these two, right? So let's say you succeed in that and you have a first pivot here. Then let's say this entry is also non-zero, or one of these two entries is non-zero. If one of them is non-zero, you can of course save Gaussian elimination by exchanging the rows. But let's say you get one of these entries to be non-zero, and you get that to be the second pivot, and you manage to erase this entry as well, and you get a 0 here. And then finally, we're hoping that this is also a non-zero entry, in which case you will get 3 pivots, right? So the maximum rank of this matrix is 3, right? And of course, other possible ranks of this matrix can be either, so maybe this is a 0 entry, in which case you get only 2 pivots, or if this is a 0 entry, in which case you get only this pivot, or all the rows are 0 and you get no pivots, right? So anything less than 3. So possible ranks are less than and equal to 3, right? Okay, so that's a possibility. And what do we have when we have that possibility? So when we have, let's say we're trying to solve ax equals to 0, and Ax equals to B, in a case where we have the full rank, when the rank of the matrix is, when the rank is equals to 3 for a 3 by 3 system. And notice that for a 3 by 3 system, the maximum rank is 3, which means for an n by n system, the maximum rank is actually to be n, right? So in the case when the rank is n, what do you have? The first thing that you can notice is that there are no free variables, right? There are no free variables because there is no row that is completely zero. There is no, you can, if you have any right hand side here, right? If you augment it and you had some right hand side B1, something happened to B2, but let's say there was B2, B3, and you can always solve these equations by back substitution and you'll get a unique solution, right? So for any right hand side, you will get a unique solution, a unique solution to Ax equals to B if there's a non-zero right hand side, and you will also get a unique solution to Ax equals to 0, right? And that unique solution for A equals to 0 is just the trivial solution, the trivial solution to Ax equals to 0, right? Because you will get non-trivial solutions to Ax equals to 0 only when you have free variables. If you set some variable to be free, and we saw this in the last lecture, and if you don't remember how we get non-trivial solutions, you can always go back to that lecture and check it out. But the idea is when you have no free variables, then you have a unique solution and you have only the trivial solution to Ax equals to 0, right? And that's the idea. So that's what happens when you have a full rank matrix, at least in a square by square system, in a square system, right? And the second possibility is if your rank is less than n, right? So for example, it was 2 or it was 1, then you start getting free variables, right? Now, when you start getting free variables, let's check that out. What happens is, take this and we put it here. Okay. So when you get free variables, what actually happens is either the third row becomes 0 or both of the second and the third row become 0, and you get x3 is free, right? So if x3 is free, what happens? The first thing that we noticed in the last lecture was that when x3 is free, you start getting non-trivial solutions, right? So you get non-trivial solutions to Ax equals to 0, which means you will have you will have infinitely many solutions to Ax equals to 0. And this is something that we saw in the last lecture, which is we got solutions of the form such as x is equals to some alpha times some vector, right? So you got a line or you got a plane through the origin, depending on how many free variables you had, right? So that's what happens. Maybe you can have even like 2 rows which are 0. So I can have this row to be 0 and this row to be 0, in which case I start getting 2 free variables and I get a line through the origin, right? So Ax equals to 0 gives me infinitely many solutions. That's the first thing. The second thing is what happens to Ax equals to B, right? And Ax equals to B is actually important here. It's not as clear cut as Ax equals to 0 because the problem is on the right hand side. You have some B1, some B2, and some B3 at the start of Gaussian elimination, right? So you better get a situation in which when you do the Gaussian elimination, remember that B2 and B3 don't remain the same. When you do row operations, you end up getting something like B2 minus 2 times B1 or B3 minus B1 plus B2, something like this, right? So these values change. And so the idea is that for you to get a solution to this problem, you should have these conditions would need to be satisfied. And we codified that condition by saying that B should be in the, it's solvable if B is in the column space of A. only then you can solve this. When B is in the column space of A, then you get solution. How many solutions do you get? You get infinitely many solutions. Infinitely many solutions. And we saw that at the end of the last lecture is that the infinitely many solutions are of the form you get a particular solution, and then you can add the solutions to the solutions to ax equals to 0, right? So you can add that null space solution to any particular solution and you'll get infinitely many solutions to ax equals to b, right? That's when it's solvable. And when it's not solvable if b is not, so this is, the symbol says it's a member of, and I'm saying it's not a member of the column space of A, right? So these were the symbols that I made for column space of A. This entire thing, you can just write it as B is a member of the column space of A, right? So that's everything, literally everything that you can say about a square system. When you solve it? How many solutions will you get? That's, if you want a one-page summary of when can you solve a square system, that's literally it. There's nothing more to it. You do Gaussian elimination. If you get n pivots, if you get all of the pivots, you'll get a unique solution to Ax equals to b. You'll get a trivial solution to Ax equals to 0. But if you get less than n pivots, then you have a problem, right? Then you have free variables and you will start getting non-trivial solutions to Ax equals to 0. And Ax equals to b will be sometimes solvable and sometimes not solvable. Okay. All right. So this is putting everything that we know into one place. Okay. So now let's talk about, we're also ready to talk about rectangular systems now, right? So rectangular systems. And so let's first talk about, so rectangular systems can come in two varieties, right? The first variety is when you have lots of columns. So let's say you have, these were the rows and these were the columns. And in this case, I'm saying m is less than n, right? So maybe you have 3 rows, but 10 columns. Or so in this case, you have the equations. So m is the number of equations, right? So the equations are lesser than the variables. You have more variables to solve for and you have just a few equations to satisfy. The other condition for rectangular systems is something like this, where you have more rows, right? So you have m greater than n, in which case you have more equations to satisfy as compared to variables, right? And these systems can arrive in different situations. These systems such as this more commonly arise in linear regression problems when you're trying to fit a line through a few points, right? You can see that. But let's try to, yeah, okay. So here's the idea. Let's first talk about the first case. Let's talk about m less than n and what happens, right? So we have lots of, let's say, I'm going to take a prototype. It doesn't need to be 10 or something, but let's start by taking 3 and let's say we have lots of columns. You can have more, of course, but yeah. Okay, so now let's ask the question, what's the maximum number of pivots I can get, right? So if I start doing Gaussian elimination, then I can eliminate these two entries. Then this is the first pivot that I get. Then I can eliminate this entry. This is the second pivot I get. And at this point, notice that if I get this to be non-zero, that's all the pivots that I can get. There is no further Gaussian elimination that I can do. So if I have m rows, there were 3 rows, right? In this case, the maximum rank can be equals to m, right? So in this case, what we're noticing is this matrix can never be full column rank. That is, its rank never be equals to the number of columns because you just have fewer rows, and Gaussian elimination proceeds by doing row operations. The row operations are limited to these 3 rows, in which case that just means you only get 3 pivots and you're done. So the maximum rank that you can get is M, and of course the possible ranks that you can get is, of course, if this was a 0 entry or if this was a 0 entry, then the possible ranks are less than n equals to M. Okay, that's the first thing that you need to notice, which means you're immediately in a situation, even when you get the maximum rank, your maximum rank is less than M is always, in this case, M is less than N, right? Which means you're always going to, your rank is less than, your rank is less than N, and you're sort of in that situation where you were before in the case of a square system where your rank was less than N, right? Your number of pivots was less than the number of columns that you have, which means what immediately happens is that you always get free variables, right? So at least we know for sure that every variable after this one is going to be free. You can get more free variables, right? If this becomes 0, then even this becomes a free variable, right? So these two become free. So you'll always have free variables in your case when you have rank less, when you have even a full rank matrix, or you have a rectangular matrix, right? When M is less than N. Okay, so if you always get free variables, which then that means that you will always have non-trivial solutions to Ax equals to 0, right? And again, Ax equals to B can either be solvable, so you can solve it if if B is in the same condition as before, if B is in the column space of A, and it's not solvable, right? You get an inconsistent system if B is not in the column space of A, right? So you can just imagine what happens is that when you get a system like this, right, and you have some pivot, let's say this is a pivot, this is a pivot, and this is a pivot, and these are some entries over here, blah, 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 blah. Okay, and if you augment the 0 matrix, the 0 vector here, right, if you were dealing with the 0 vector, then of course the solutions that you will get will be in terms of these free variables, right? So this is x3 and this is x4 and x5, right? And the solutions will be in terms of the number of solutions you will get. So if you have a solution that is in the null space, the null space means all the solutions to 0, they will be in the form of, they will be a linear combination of the free variables, right? And if you don't understand how this happens, you can check the previous lecture, but I can just give you a little example here. For example, if I look at this equation, I say something times x2, right? Let's say alpha 1 times x2. Let me erase that. Let me just write it properly. Let me give you an example, right? I'm giving you an example that this last equation can be something times x2 plus something times x3 alpha 1 alpha 2 plus something times x4 plus something times x5 equals to 0, right? Because that's the equation. And now you can solve for x2. You can say x2 is actually alpha 2 x3, and you subtract it, right? You can write x2 in terms of x3, x4, and x5, and you can just divide it by alpha 1. So you get every variable x2 and x1 and let's call this x0, x1, x2, right? All of these variables can be written in terms of the free variables, and I showed you how to write that you solve each of these equations in terms of the free variables, and then you separate them and you write them something like x3 times some vector plus x4 times some vector plus x5 times some vector. This is something I showed you in the last lecture, so if you're confused about how we got there, you can just check out the previous lecture. Okay. But that's the idea. The idea is that it's either, so Ax equals to 0 will have non-trivial solutions because you always have um, free variables, right? Okay. And what about Ax equals to b? Ax equals to b, of course, is then there's a problem in Ax equals to b because let's say you had the 3 pivots, okay, and then you had some entries, and now blah, 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 blah. Okay, and what about Ax equals to b? So in this case, now we have, let's say there was b1, there was b2, and b3. And now notice that if you want to solve this third equation, you can solve it in terms of b3. Something happens to this b3, of course. There are some row operations that are done. So maybe they're not the first b3. Let's call them b2 star and b3 star, or let's just undo that. Let's call them b1 prime, b2 prime, b3 prime, right? The b1, let me just write them. What do I mean by b2 prime and b3 prime? Are the right-hand side after you are done with elimination, right? I showed you in the last lecture that when you're doing elimination, these right-hand sides will also change because you've augmented the right-hand side with it. But now, can I ever have a situation where I can't solve these equations? It doesn't seem like that, right? Because it seems like I'm not getting these problematic rows, right? Like in this case, these 0 rows are not appearing, right? So if my rank is equals to m, then I can always find a solution. And that's because this last row is easily solvable, right? So if this was some variable and these were the free variables, you can just leave this on the left-hand side, and on the right-hand side, you get b prime plus all the free variables and their coefficients, right? And this is the solution that you will get to the last equation, right? And then you can plug that into the second equation, and then you solve it for this variable, right? So this was x1, this was x2, this was x3. So you can solve, what I'm trying to say is x4, x5, x6. You can solve x1, x2, and x3 in terms of x4, x5, and x6, right? And these are just constants, right? b1, b2, b3. These are just numbers that will just appear on the right-hand side. So your solution will look something like x particular plus some linear combination of x4, x5, x6, right? These are my solutions to Ax equals to, right? When I have a full rank matrix. Well, full, what do I mean by a full? In this case, it's a full row rank, right? Because it can't be a full column rank matrix. But in the case when rank is less than m, then you have a problem, right? For example, I get 1 here and the rest of the entries are 0. So I get a 0 here, right? 0, 0, 0, 0. And notice all of this entire row should be 0. Because if any of these other rows, let's say, if I get this to be non-zero, right? Then you have the next pivot. Then you can solve it for this. So the only way that you're going to get just one pivot is if the second row and the third row are entirely eliminated after elimination, right? So this is the situation that happens, that you get only one pivot, right? So pivot is equals to 1, rank is equals to 1, and in this case, you can now run into a problem where b1 prime, b2 prime, and b3 prime, right? Whatever these numbers are, these numbers have to be 0. After elimination, if you don't get, if 0 is equals to b2 prime, and if 0 is not equals to b3 prime, I can't solve. But if 0 is equals to b2 prime, whatever number you get on the right hand side after elimination, and 0 is equals to b3 prime after elimination, then you can solve And you can again get infinitely many solutions. So infinitely many solutions. And these solutions arrive, and these solutions, so for example, so when you do have, right, when it's solvable, in the case when it's solvable, then what you get is x2, x3, x4, all of these, every variable other than x1 is free, right? Or other than, let's just say, other than the pivot variables, other than the pivot is free, right? So maybe you get one pivot, maybe you can get two pivots, but that's depending on the kind of system that you get. So let me just, as an example, just write down different cases that may occur. So let's say you get this case or you get this case, right? In this case, let's say I get, if let's say there was a non-zero entry here, then you have two pivots. So the rank in this case is 2. Let's say if I get a non-zero entry somewhere here, right? Let's say I get a non-zero entry here and I get a pivot, then in this case also my rank is equals to 2. And if something in the third row is also 0 or non-zero, then you get a full row rank matrix, and then you're no longer in rank less than equals to m case, you're in the rank equals to m case, right? So that's the idea. Okay, so these are the possibilities that you can get in a m less than n matrix in a sort of a lengthwise long rectangular matrix, right? Okay, let's talk about m greater than n matrix, right? So we're talking about now these tall matrices. Let's call these matrices tall, and let's call the other matrices wide, right? So we've discussed wide matrices. Now let's talk about the tall matrices. Okay, so what do we have here? Let's say we have 3 columns. This can of course be different, but I like dealing with this. Okay, so what's happening here? Let's talk about what can happen when you do Gaussian elimination on such a matrix. The best that you can hope for, the max rank in this case. So if these are n is equals to 3 in case, m is equals to 5 in this case, the maximum rank that you can get is, okay, first row, second row, third row. Let's say we managed to eliminate all of these entries, right? Let's say we managed to eliminate all of these entries, right? So let's say this was all 0. I'm not going to put anything here. It's understood that these are all 0. So the maximum rank that I can hope for is 3. So this is, you can get a full column rank in this case, but you can't get full row rank, example, right? So the maximum number of pivots that you're going to get, so the max rank in this case, maximum rank is equals to n in this case. In the previous case, the maximum rank, mentioned this? So in the previous case, the maximum rank, so this was maximum rank was equals to m, number of rows, and in this case, the maximum rank is equals to n, right? Okay, so what we know about the system. So the first thing that I can see is if my columns have been exhausted, I don't have free variables. So we don't have free variables in the case when I have maximum rank. When rank is equals to n, I don't have free variables, right? That's the first thing that happens when you get all of the pivots. Okay, what about ax equals to 0? So ax equals to 0 will then have, if there are no free variables, then ax equals to 0 will have a unique solution, right? You get a unique solution to ax equals to 0 because there's no free variables, everything has been eliminated, there's 0, 0, 0. On the right hand side, you can see these equations are 0 equals to 0, 0 equals to 0, and you can just solve these 3 equations for x1, x2, and x3, and you're done, and you get a unique solution, right? Okay, so Ax equals to 0 is easy. You get a unique solution. Now, what about Ax equals to b? So rank is equals to n, and I'm talking about Ax equals to b. So we have this tall sort of a matrix, right? And let's say we augmented the right hand side and we're done with elimination, and so there was some entries here, right? Some entries here, some entries here. This was my pivot, this was my pivot, this was my pivot. All the rest of the rows are 0, 0, 0. And this is b1 prime, this is b2 prime, b3 prime, right? These are again entries after elimination, not the original right hand side, the right hand side that I get after elimination. And so notice that these are all zeros, right? 0, 0, 0, blah, blah, blah. And now these entries b4, b5 prime, b6 prime, you want to hope that the only way that you're going to be able to satisfy all of these equations is that these really need to be satisfied, that this b4 prime should be equal to 0, this b5 prime should be equal to 0, this b6 prime should be equal to 0. That is, when you do elimination, not only are you hoping that if all of these rows become 0, then these things on the right hand side should also become 0, right? So when you're doing row operations, you're hoping row operations should give zeros on the augmented right hand side below the pivot equations, right? And I'm now calling them pivot equations. That's not really a real thing, but the idea is that these were the pivot, right? Because pivot rows, let's call them pivot sort of rows, right? So I'm hoping that below the pivot rows, I get zeros on the right hand side as well, because if I don't get zeros, then I get an inconsistent system. And so if any of these conditions is not satisfied, so basically the problem is that you have lots of equations to satisfy, with few variables, right? With few variables. And you can sort of think about this in terms of, I don't know, maybe, so let's say you have, yeah, I think that's, why did I put an apostrophe here? Okay, so I think that's the best thing that we can say, is that there are lots of equations to satisfy, but there are only few variables, and you better hope that all of these rows are sort of depending on these rows, so that when you do row operations, all of them become 0. Otherwise, you just get an inconsistent solution and you can't solve them. So there's two possibilities, right? You can solve if the rows are, let's say, if the rows below the pivots, if the rows below the pivot variables, and I think I'm going to do some examples today, so just all of these ideas become concrete. But yeah, if the rows below the pivot rows are 0, right, along with the augmented column, right, this is when you get a consistent system, and you can then solve Ax equals to b, right? And so in this case, Ax equals to b will have a unique solution. So Ax equals to b has unique solution. But of course, that seems very unlikely, right? Most of the cases, most of the times, if you just try to satisfy lots of equations with only 3 variables, you're going to run into a problem, right? And so what can happen is you will, let's say, what can I say? So they're inconsistent if the rows, if the augmented column has non-zero entries below the pivot rows. right? So that's something that we can say about the system. So when you try to solve the system, if you start getting some equations that are not satisfied, then you will get an inconsistent system, and then you will have no solution to that problem. So that's the possibility. That's what happens when you have a full row rank, or sorry, a full column rank matrix in this tall matrix, right? There's just one last case to discuss, and that's the case when your rank, so the possible rank in this case, we knew that the maximum rank can be n, but the possible ranks can be less than n, right? So less than n equals to n. So now let's talk about this case where you have a tall matrix and your rank is less than n, right? So let's say you had one pivot and blah, blah, blah. Let's say you also have another pivot, right? And now you have just 0 rows, 0, 0, 0, 0, 0. All of it is 0, right? Let's just leave it empty. Or let's just say it's 0, 0, 0. Okay. And so again, now in AX equals to 0, what happens when you have a 0 row, but what happens to this variable, right? If this variable is not a pivot variable, then this is a free variable. If this is a free variable, then AX equals to 0 immediately has non-trivial solutions, right? Okay. And what about AX equals to B? Again, you have some right-hand side, right? It's B1 prime, B2 prime, and B3 prime, and B4 prime, and la la la. So again, you see that now what you have is you have an extra equation to satisfy, right? So B3 prime should also be 0. So if it's consistent, if it's a consistent system and all of these variables are indeed 0, then you will get infinitely many solutions. You will get infinitely many because there are lots of non-trivial solutions that you can add to your particular solutions, right? So you get infinitely many solutions. But if you have an inconsistent system, then of course you don't have a solution. And that's I think the entirety of the theory of linear systems right there. We've talked about all kinds of systems. We've talked about square systems, and it seems like we're almost done with talking about linear equations, right? So all the possible cases that you could have in Gaussian elimination, we've gone through them, right? So the first case, let me just summarize. The first case, when you have square systems, your rank can be either n or less than n. When it's n, you have these conditions for AX equals to B and AX equals to 0. You know that AX equals to B will have a unique solution. You know that AX equals to 0 will have a trivial solution. If the rank is less than n, then you get a free variable, and free variables for AX equals to 0 give you a non-trivial solution, but free variables for AX equals to B give you conditions to satisfy. And if those conditions are satisfied, that is this row is satisfied, the 0 is equals to B3, then we get infinitely many solutions, otherwise we don't get any solution, right? And the same is the case for tall and wide matrices. In wide matrices, what you get, the maximum rank can be the number of rows. And so when you do have the maximum rank, even when you get a max rank, you always get free variables, and you always have non-trivial solutions. And again, when you have free variables, AX equals to B can either be solvable or not solvable, right? So wide matrices are easy to deal with. And then, of course, you can have rank can be less than your number of rows, in which case you get some conditions to satisfy, and then those conditions need to be met. So the important thing was, in this case, even though you get free variables, you don't get any conditions, right? So in the case when rank is m, you always do find a solution when you have a full rank wide matrix. You will get no solutions only in the case when one of those pivot variables, like when one of those rows becomes 0, right? This row becomes 0, this row becomes 0. In that case, you might be able to solve it, or you might not be able to solve it, right? But if you get a full rank wide matrix, then you'll always be able to solve it, right? and the tall matrices we just talked about, right? So you can get full rank can be equals to the number of rows, but then even you get some conditions to be satisfied, right? That's the that's the entire theory about linear systems. Okay, yes. So so we've discussed rank of a matrix, and we've discussed when you can solve a system and when you can't solve a system. Um, I would suggest that you doing some examples, right? So try solving the system, try making up maybe your own system, and try solving it, right? So um, get try solving a wide system, right, where m is less than n, and try making up a system where you have more equations than less unknown, right? So try solving these systems. I think I've done some problems in the homework. Your homework is due on Friday, so make sure you're working on that. If you have any problems with the homework, let me know and we can set up a one-on-one video. We can talk about any issues that you might be having. Okay, so let me go, and now finally we're able to talk about this idea of independence. I know I said that I'm going to do some examples of these tall and wide cases. I think let's just do that on Friday when we have that Google Meet session. And then I can do a few examples of these cases and you'll to better illustrate these, right? So let's talk about some more theory for now, and let's talk about independence, right? And in particular, this term is the full term is linear independence, right? And we saw linear independence come up when we were talking about vectors, right? And we were talking about vector spanning and vectors. And I seem to have sort of completely ignored what's going on in terms of vectors, in terms of the column picture in all of this discussion, right? So let's take that example, right? Let's let's take one of these cases and figure out what's happening here. So for example, let's take the case of a square matrix with full rank. So a full rank square matrix, right? So let's say we have a 3 by 3 full rank square matrix. And when I say full rank, of course, when it's square, then the rows are equals to the columns. Then it's if you call it a full column rank matrix or a full row rank matrix, that's exactly the same thing. So let's say you have 3 pivots, right? You got 3 pivots and you wanted to solve some system of equations. And what's happening in terms of, we've talked about what's happening in terms of Ax equals to 0. We have talked about in terms of Ax equals to b. Let's now talk about in terms of the combinations of, so let's say this was column 1, this was column 2, this was column 3. And actually, well, this is not the original, right? So this is 0, 0, 0. The original matrix was, let's suppose, some A matrix, right? Which you turned into this matrix by doing some Gaussian elimination, right? Okay, so let's say this original matrix was 1, 0, 0. Let's take a and 1, 1, 0 and 1, 1, 1. That's a nice little matrix, right? Okay, and so this was the column, this is column 2, and this is column 3. Okay, and I see that, let's just take some examples. Let's say this 1, 2, 3, and this was 1, 4, and 8. And let's make this, let's ensure. So I know for sure that these two are independent. So this, this is 2 and this is 6, and if I make this 10, I believe that this should give me a Untitled matrix that is a full column matrix, right? And let's try and make sure that this is a full rank matrix, right? Let's do this example here. Okay, so let's do Gaussian elimination. Gaussian elimination tells me row 2 minus 2 row 1 and row 3 minus 3 row 1. Why did I choose 2? I chose 2 because this was the entry that I wanted to eliminate, and the first entry was 1 in the first row. So I can just immediately get rid of this entry by doing row 2 minus 2 row 1, and let's see the matrix that we get. Hopefully we get 3 pivots, so 1 1 2, and so 2 minus 2 is 0, 4 minus 2 gives me 2, and then 6 minus 4 gives me 2. Okay, the third row is 0, 3 minus 3, 8 minus 3 gives me 5, and 10 minus 6 gives me 4. Okay, so I have one pivot and I have two pivots, and I can see that I will probably succeed in finding the third as well. Before doing the before finding this, I can make things easy for myself if I just divide, if I make this pivot 1, right? So turn this pivot 1 by doing row 2 multiplied by half, right? So let's do row 2 times half, and that gives me first row is preserved, second row is 0 1 1, the third row is just this, right? So I've done nothing but multiply my second row with a matrix, a number, right? And this is the matrix that I have, and now I can do row 3 minus 5 times row 1, and this is the final matrix that I will get: 1 1 2, 0 1 1, and then finally 0. 5 minus 5 gives me 0, and 4 minus 5 gives me minus 1. So you notice that I got 3 pivots, exactly 3 pivots that I needed, right? So this is a full column or full rank matrix. Okay, so this is what Gaussian elimination gave me at the end, right? I went through this entire process, and this was A, and let's call this matrix A star, A prime, or let's just call it let's call it A prime for now. Sorry. Okay, so now I was saying that I want to look at it in terms of the columns, right? Now notice that this has a unique solution. If I augment this, if I talk about AX equals to, let's say AX equals to B or X equals to 0, I know the following. AX equals to B will have a unique solution for any B, because I don't have any conditions to satisfy, and I have 3 pivots, and I can solve exactly for any pivot, right? And AX equals to 0 will have the trivial solution, trivial solution. What does that tell me? It tells me that my B, every B is in the column space of A, which means columns of A are actually, if every B, and we know that we're in 3-dimension space, right? If we're in 3-dimension space, let's say this, okay? Let's just turn this on because this used to be a nice little feature. Okay, so if I'm in this direction, if I am in 3 dimensions, right? And if I can solve AX equals to B for any B, right? Remember the column picture. The column picture said that AX equals to B is actually x1 c1 plus x2 c2 plus x3 c3 is equals to B. That is, we're looking for these scalars such that when we add these together, you get B. So B is a linear combination of these columns of A, right? So C1, C2, C3 are columns of A. And when you get these 3 columns to be completely, if you're in this situation, you can solve it for any possible B. It means these 3 vectors together are giving you the entire space, right? So the term that I use, so I said that this will give me the entire space. You take one, let's say this vector was in this direction, and this vector was in this direction, and this vector was in this direction, and together they give you this entire 3-dimension space, right? Okay. And so I want to make this idea of independence independence, right? Concrete. So what do I mean by independence, right? So let's define independence. So the definition of independence is as follows. One thing that I can say about independence is, let's define it in the following way. Vectors x, vector c1, right, or v1, whereas v1, v2, v3 are linearly independent if no vector can be written if or rather let's write it as, if none of these vectors, if none of them can be written as a linear combination of the others, This is a rough definition, linear combination of the. This is a rough definition. This is not exactly precise, but we're going to make it precise first by thinking about what this means. So let's say I have a vector. This was v1. If I want the other vector v2 to be independent, then it can't lie on this line, right? If v1 and v2 are independent, then v2 does not lie in the line covered by v1, because otherwise v2 and v1 both will be on this line and you won't get a two-dimensional plane, you'll just get this line, right? So to get a second vector, v2 needs to be outside this line somehow, right? So v2 is outside this line, and then you get a, so for example, when I say does not lie, what does that mean? That means v2 is not a scalar multiple of v1, because if it was in the line, then this would be true. Okay. All right. Now let's say we make this line. Let's get this line made. Sorry. Oops. So let's try to make it nicer this time. Okay. Now you have two vectors and they're independent, and if they're independent, they're going to form a plane, right? So if you take all possible linear combinations, recall that taking linear combinations of two vectors, right? If I take this vector, add it to this, I get this vector as well, and I can get this vector, and any vector on this two-dimensional plane can be covered by linear combinations of these two, right? So now if I want next condition, if I want v3 is independent. So if I want v1, v2, v3 to be independent, then v3 should not lie in the plane covered by v2 and v1, right? That's something important that I want, that v3 should not be in this plane, which means I want v3. So let's say this is a plane that was made, and this was v1 and v2. They were inside this plane, and now I want for my v3 to be outside. It's sort of coming outside of this plane, sort of, right? Outside the page. Okay, and so that's only possible. When is that possible? When v3 is not a linear combination alpha 1 v1 plus alpha 2 v2, right? So this is what I meant when I said that none of them can be written as a linear combination of the others, right? So what does it mean? So v2 is not a linear combination of v1, and v3 is not a linear combination of v1 and v2, right? And so notice that in this condition that I've written, right, what I'm actually saying, there are no, if we rewrite this equation, right, if I rewrite this equation as alpha 1 v1 alpha 2 v2 and bring v3 to the other side, say minus v3 equals to 0, what I'm saying is that there should be no combination. I should not be able to find no linear combination of these three vectors should equal 0, should equal 0, right? Because if any linear combination of them equals 0, then I can take one of them to the other side. So for example, say I have 5v1 plus 2v2 plus 3v3 equals to 0. Let's say if that's the case, then I have a problem, because I can say that 3v3 is equals to minus 3v3 is equals to 5v1 plus 2v2, and then I can just take minus 3 to the other side, and I say v3 is minus 5 upon 3v1 plus, minus 2 upon 3 v2, right? So it should not be the case for any scalars alpha 1, alpha 2, alpha 3. There should not be any such scalars, right? Except when all scalars are 0. When all scalars are 0, that's something that you can't avoid, because if you have zeros, right? So if alpha 1 is 0 and alpha 2 is 0 and alpha 3 is 0, then what you have is 0 times v1 plus 0 times v2 plus 0 times v3. But that's fine, right? Because I can't use these zeros and say that v3 is some linear combination, because this equation is just saying 0 equals to 0. That's fine. But even if one of the scalars is non-zero, then we have a problem. Why do we have a problem? Let's talk about when two of them are 0, right? So let's say alpha 1 is 5 and alpha 2 is 3 and alpha 3 is 0, right? So when two of them are non-zero, so I can say 5v1 plus 3v2 is equals to 0, then we have a problem, because I can say that v1 is equals to minus 3 upon 5v2, and that's a problem because that v2 is in the line of v1, which is the first case that we wanted to avoid. We didn't want v2 to be in the line of v1 or v1 to be in the line of v2, right? That's something that we wanted to avoid. So even if when you have two non-zero scalars, then you have a problem. Let's say when alpha 1 is equals to 5 and alpha 2 is equals to 0 and alpha 3 is equals to 0. If one of them is non-zero, right? When one of them is non-zero, 5v1 equals to 0, then you have a special case. Then you actually have the case where one of the vectors is 0. So what we're talking about is 0 was actually the 0 vector. And the 0 vector in a list is dependent, because 0 vector is in the line of, say, v1 and v2, right? Let's say this was v2, then this line cut by v2 includes the 0 vector. So even in this case, they are not independent, right? So let me just recap what I was saying. I was saying that I want them to be independent. I want them to be outside each other's spaces, right? So when I made the space for v, I wanted v2 to be outside that line. So I didn't want v2 to be equals to some alpha times v1. When I wanted v3 to be outside the plane, then I didn't want v3 to be equals to some linear combination, right? And then I turned this equation, I said, let's rewrite this equation, let's bring all the vectors to one side, right, like this. And let's just call them, this is alpha 1, this is alpha 2, let's call this alpha 3 as well, right? And we should not have, if I look at it in terms of this equation, then none of these alpha 1s and alpha 2 and alpha 3 should combine, give me a linear combination that is equals to 0. Because if that's possible, for example, 5v1 plus 2v2 plus 3v3 gives me 0, then I can say that v3 is some linear combination. And when that happens, right? When this happens, I'm essentially saying that V3 is in the plane. V3, so this tells me that V3 is in the plane of V2 and V1, and I don't want that. So there should not be any non-zero terms that give me 0. Even if two of them are non-zero, I have a problem. V2 comes to the line of V, right? So there's a new definition that I'm now ready to make of independence, right? So the definition of independence that I want to make is the following, is that there should be no non-zero scalars alpha 1. Okay, let's start from the beginning. I'm saying v1, v2, v3 and vn are linearly independent if alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus all of these alpha n vn is equals to 0 only if all scalars are 0. All scalars are 0, right? Another way that you will find this in the Stephen Leon book or maybe in Gilbert Strang's book is to say that alpha 1 v1 plus alpha 2 v2 plus dot 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 alpha n vn is equals to 0 should only happen if and only if, right? So if and only if alpha 1, alpha 2, all of them are 0, right? And why is the case? Why is that the case? Because we just saw that even if one of them is non-zero, then we have a set of dependent vectors, right? If two of them are non-zero, one of them is in the line of the other. If one of the scalars is 0, then we have the 0 vector in the list, and that's problematic, right? So that definition. So that's the final definition of independence, is that all of them should only equal to 0 if and only if alpha 1, alpha 2, all of them are 0. Okay, that's fine. And this is nothing new. This is something that you've already done. And let me show you how you've already done this before, right? This definition of linear independence that I've just sort of came up with, let me show you how this is connected. This is connected to ax equals to 0, right? Let's say the matrix is A such that V1 is the first column, V2 is the second column, and I have all of these Vn as my n columns of A, right? So these are n columns of A, right? And let's say I'm trying to solve the system. Let's say I'm trying to solve Ax equals to 0, right? So I'm trying to solve this. Let's say this was x1, x2, and xn is equals to 0, 0, right? I know that I can view, so this is the equation that I'm trying to solve, Ax equals to 0. And now I can write the left-hand side as a linear combination of these vectors. So x1 v1 plus x2 v2 plus dot 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 xn vn is equals to 0. And that's something that we just talked about, right? This is a linear combination of the columns of A being equals to 0. This was a linear combination of some vectors v1 to vn equals to 0. And we said that v1 to vn is 0 if and only if all these scalars are 0. Now if all these scalars are 0, so let me say the columns of A are linearly independent if and only if x1 is equals to x2 is equals to all these scalars should be 0. This is the condition that we just derived, right? This is the definition that we just settled on, that scalars need to be 0. But if all of these scalars are 0, what does that tell you about the solution to x equals to 0? It's telling me that the solution x1 dot 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 xn is just the trivial solution. So in other words, it's saying that if all of them is 0, that means x equals to 0 only has the trivial solution. That's the key connection here, is that the columns of A are linearly independent if and only if this is true, that these x1s, x2, xn, these are all equals to 0, and that just means that Ax equals to 0 only has trivial solution. So this is something that I want to write down, that the columns of A are linearly independent if and only if. So let me just make an if and only if symbol, that Ax equals to 0 only has the trivial solution. So these are equivalent statements that we've just seen, right? These are two lenses to the same problem that we are seeing. Okay. I think I'm going to stop the lecture at this point. We're going to talk more about independence, linear independence, but I think this is a good point to stop, because let me just tell you what we've achieved so far. When we started talking about dependence, I wanted to define independence, linear independence, in a systematic way, in a mathematical way. And we settled on this definition. We said, after going through all the working, we said that a set of vectors are linearly independent if their linear combination is only 0 when the scalars are 0, right? So their linear combination is 0 if and only if these scalars are 0. Otherwise, what happens is one of them can be written as the linear combination of the others, or one of them is just the 0 vector, which is again does not, if the 0 vector is in my list, it gives me a set of dependent vectors, right? And finally, we just saw how that definition was really connected to Ax equals to 0. Because if you have these vectors, and if you just see them as the columns of matrix, right? So if you have v1, v2, vn, you're trying to decide whether they're independent or not, then you make a matrix out of these vectors, you stack them column wise, and you try to solve Ax equals to 0. If they're linearly independent, then these x1s to xn should only be equals to 0, which means this system is only going to have the trivial solution, right? That's what we've achieved. We said we've defined linear independence, and then we've shown linear independence only happens when this matrix has only the trivial solution. It's one and the same thing. Okay. All right. I think that's it for today's lecture. Let me know if you have any questions, any confusions. We did a lot today, especially in the rank part, and then we talked about linear independence. We're going to take these ideas forward, linear independence. The next lecture is going to be about span and vectors, right? So we're getting sort of to the core ideas, and it's just, you can start to appreciate that these are all the same ideas, but being said in lots of different ways, and just trying to a lens that is convenient. Sometimes we look at it in terms of matrices, in terms of rank of the matrix, and sometimes we look at the problem in terms of the vectors that make up that matrix, right? It's really an interplay between vector spaces and matrices.